Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Control Systems. Today we'll start chapter 10, and this is the last chapter. In this chapter we'll see new techniques, okay, to study the system. So the frequency response is the steady-state response of system to sinusoidal input. In frequency response methods, the frequency of the input signal is varied over a certain range, and the resulting response is studied. So here in the input to the system, we'll not use step input as for the steady-state error, but we do the sinusoidal input. Okay, and why we use the sinusoidal input is to study the system. So we'll have this connection as shown here. So the input will be, so here you have the input. So this is the input, okay. And we'll use this oscilloscope to generate sinusoidal input. Okay. After that, we'll connect in the output another oscilloscope to to generate. We don't use oscilloscope. So to generate signal we use generator. Okay. It's a generator. Okay. You can use voltage generator. And here we have the oscilloscope to display the output. Okay. So here we display the output. So for sure the output should be also sinusoidal signal, but for sure with different, maybe with different amplitude. Okay, with different amplitude. So in the steady state, sinusoidal inputs to a linear system generate sinusoidal responses of the same frequency. So the system, so here the output and the input will have the same frequency. But they will differ in the amplitude and phase angle from, so the output will differ from will differ in amplitude, so the amplitude will be different, and the angle also. That means if the input is for sine, if the input is sine WT with an amplitude AI, so the output is with AI sine, so the output will be AO sine WT minus phi, okay, or plus phi. So there is a phase angle between the two signals. So these differences are functions of frequency. So it's plus phi here. Minus, it's plus, should be plus, because it will be just after the input. So it will be plus phi. So sinusoids can be represented as complex numbers called phasors. So we can use the complex representation. We can, for example, use the exponential j phi, or exponential so we can use the exponential j phi. So the magnitude of the complex number is the amplitude of the sinusoid, and the angle of the complex number is the phase angle of the sinusoid. So that means if we use the, for example, M1 cosine WT plus phi can be represented as the amplitude M1 and the angle is phi 1, where the frequency W is implicit in this representation. Okay, it's implicit. We cannot see W in this representation. A system causes both the amplitude and phase angle of the input to be changed. So also the system has amplitude and phase angle, and this system will cause both amplitude and phase angle of the input to be changed, and you will see why. Okay, we see why and how. So therefore the system itself can be represented by a complex number. Okay, the system also could be represented by a complex number. So the product of the input phasor and the function. Sorry, any question, please? Any question, please? Ahmed Samah, Ahmed Faiz, is it clear, please?
Yes, Doctor, clear.
Okay. So the product of the input phasor and the system function is the phasor representation of the output. So as example, here we consider this mechanical system, and the excitation here for this mechanical system is the displacement. Sorry, it's the force. Okay, this is the input, as you know. So this is the input. The excitation is the force. Yeah, okay, it's the input. And this input has amplitude Mi, frequency W, and phase angle phi I. The displacement now is the output, and this displacement has an amplitude Mo, the same frequency and a different phase angle. Okay, so the system also could be represented. So the system could be represented as amplitude and phase angle. Why? Because you will see later that this Mo equal Mi times M from the system. Okay, and phi O, the output phase angle, equal phi I plus phi W from the system. So if the input force Ft is sinusoidal, the steady state output response x of t of the system is also sinusoidal and at the same frequency as the input. So here we have an example. So here this is the input, okay, and here we have the Mi, which is the maximum amplitude Mi, phi I is the phase angle. Okay, so this is the input. The output, so for the output, the maximum amplitude is Mo equal Mi times M, and O equal phi I plus phi. So assume that the system is represented by the complex number M phi. The output is found by multiplying the complex number representation of the input by the complex number representation of the system. Okay, so the amplitude Mo equal M times Mi, and the phase angle phi O equal phi plus phi I. So the combination of the magnitude and phase frequency responses is called the frequency response. Okay, so this is the frequency response, and we'll see how to study this frequency response. So there are two ways in this chapter here, the body plot and Nyquist plot. So the body plot consists of two graphs. One is a plot of the logarithm of the magnitude of a sinusoidal transfer function, and the other is a plot of the phase angle. So this is the body plot. It has two graphs. So both graphs are plotted against the frequency on logarithmic scale. So the first graph is here as shown is magnitude. Okay, and the unit is decibel because we'll evaluate 20 log m. Okay, magnitude. And the second graph is the phase angle in degrees, and as shown here, both graphs will be plotted versus frequency, and the frequency is in radian per second. And here we use the logarithmic scale. So that means we start from 10 to the power 0, then 10 to the power 1, and 10 squared. So this is the body diagram, and for sure we can use MATLAB to plot both this graph using the function body. So we'll see how to use it. Just for your knowledge, so here we call this unit as decade. Okay, this part is decade. So here there are some basic factors of transfer function, such as the gain, the integral and derivatives, derivative factors, first order factors, and quadratic factors. So for here, if we have g of s equal 20 times 3s plus 1 divided over s times s plus 1 times s squared plus 5s plus 2, the question now is how to plot this the body diagram by hand without software. Okay, so we should know how to plot for the gain 20, also how to plot for 3s plus 1, how to plot for 1 over s, how to plot for 1 over s plus 1, and so on. Okay, so let's start by the gain. So the log magnitude curve for a constant gain k is a horizontal straight line at the magnitude of 20 log k decibels. So this is the unit. Okay, it's decibels. The phase angle of the gain k is 0. And the effect of varying the gain k in the transfer function is that it raises or lowers the log magnitude. Okay, so this gain can only raise or lower the log magnitude curve of the transfer function by the corresponding constant amount, but it has no effect on the phase curve. Okay, so the gain has no effect on the phase curve. So for example, if we have k equal 5, 20 log k equal 14 decibel, and we can represent this 14 decibel in the magnitude curve as a line at 14, okay, at 14 decibel. And for the phase, it has no effect, okay, because it's 0. So here the phase is 0 for k equal 5. Now, if we have integral and derivative factors, jw to the power plus minus 1. So as you know, the derivative is jw, and the integral is 1 over jw. So this is the integral. So the integral is 1 over jw, and the derivative is jw. So for the first case, derivative factor gs equal s, so s equal jw, and the magnitude will be 20 log w. That means it will be it will depends on the value of w. So here log 0.1 is minus 20 decibel, and so on. For if w equal 1, so you will get 20 log of 1 equals 0. Okay, so here we have two, we have a slope. We have slope by it's 20 decibel per decade. Okay, so we can, how to represent it? Yeah, for the phase also, for the phase it's tan inverse of w over 0, so which is 90 degrees. So here we can represent the 20, since we start from minus 20 to 0, from minus 20 to 0. So it's as shown in this first curve. So we start from minus 20 here, decibel, to 0, okay, for 1 per decade, right? And this is the decade, as you know. This is the decade. Okay. So this is for the derivative. Now for the phase angle, for the phase of derivative is 90 degrees. So we can present it as shown here. Okay, it's a line. Okay, now for the here we will use this characteristic for integral. So as you know, 20 log n equal minus 20 log 1 over n. Okay, so we use this property to draw the integral, the body plot for integral. So for integral factor, the slope of the magnitude line would be same but with opposite sign. Okay, with opposite sign. The phase angle also for the integral is minus 90 degrees. So here for the magnitude, it will start from 20. Okay, here for the table. So if we, so this is for derivative, right? This is for derivative. For integral, it will start from 20. Okay, for integral, it will start from 20, 14, 8, 6, and so on until 0. So it will be, the slope will be minus 20 decibel per decade. Okay, it will be minus 20 decibel per decade. And this is the decade. Okay, it's from 20 to 0. And for the phase, it will be minus 90 degrees, as shown in this figure. Now for the first order factors, if you have 1 plus j omega s, in this case, what will be the magnitude, or what will be the body plot? So here we'll have two cases. If for low frequencies, that means if w is less than 1 over t. If w is less than 1 over t, so in this case, the magnitude is 0. However, for high frequencies, that means if w is greater than 1 over t, so here the magnitude becomes 20 log wt. Okay, so we have two cases. For the phase angle, when w equals 0, so when w equals 0 here, the phase angle equals 0. When w equals 1 over t, phase angle equals 45 degrees. And when w is infinity, so here we'll have 90 degrees as phase angle. So how to draw now? For example, if we have s plus 3, so s plus 3, here so what's the meaning of s plus 3? That means, so here for w equal 3, if w equals, how to read w here equal 3, so here w equal 1, okay, and here you have 1 2 3, so this is w equal 3, okay. So for w equal 3, the you'll have 0 because it's low frequency, okay. So for low frequency, that means if w is greater than 1 over t, and 1 over t equal 3 here, when s for this here, okay, so 1 over t is 3, isn't it? So we have 1 plus dw t, and here since we have 3, that means we should divide by 3 to get t, okay. So t equal, when w, I repeat, when w is greater than 1 over t, that means from 0, w will be from 0 to 3. In this case, the magnitude equals 0. Then for high frequencies, you will have 20 log Wt, and 20 log Wt is 20 decibels per decade, as you know. So that means between this point and this point, it will be 20 decibel. So this is the decade here. Okay. What about the phase now? For the phase, as you know, there are 3 points. We can draw the curve using these 3 points. So at 0, at 3, and at infinity. So at 0, we have 0. At 3, we have 45, and at infinity, we have 90 degrees. Okay. Now, if we have first order factor with the power -1, that means you have 1 over jwt plus 1. Okay, so it will be minus, the magnitude will be -20. And for low frequencies, that means if w is less than 1 over t, so the magnitude will be 0. And for high frequencies, the magnitude will be -20 log Wt. And for the phase angle, it will be for w is 0 degrees, for 1 over t is -45, and for infinity is -90 degrees. And here there is another example. So when g of s equal 1 over s plus 3, so we have to look at w equal 3. So if for low frequencies, the magnitude is 0, and for high frequencies, the magnitude is -20 decibel per decade. And for the phase angle, we have just to use these 3 points. Now, as example, let's combine the what we already saw until now. So here we have 20, we have s, and you have 1 over s plus 10. Okay, so that means the gain is 2, derivative factor is s, and the first order factor in the denominator is 1 plus 0.1 plus 0.1 s. So for the gain factor, 20 log 2 equals 6 decibel. Okay. For the derivative, 20 log W is 20 decibel per decade, and for the first factor, here 1 over T is 10. In this case, 1 over T equals 10. So if W is greater than 1 over T, which is 10, in this case, the magnitude equals 0. And when W is greater than 10 for high frequencies, so the magnitude will be minus 20 decibel per decade. Now let's see how to combine this three. You have three curves, right? You have three curves. So here k equal 2. If k equal 2, then derivative factor, and when W is less than 10 or greater than 10. So here we have k equal 2. The magnitude is 6 decibel. It's constant. We also have the 20 decibel per decade. It comes from derivative factor. And we have 0 for low frequencies until 10. We have 0 until 10 radian per second. Then we have minus 20 decibel. So now the question is how to draw the magnitude of the system. How to draw the magnitude of the system for the first part here. Yeah. How to draw the magnitude of the system now. So why we start here from minus 14? So we have 6. So let's look here. We have 6. Okay. 6. Here we have 0, and here we have minus 20. Okay. So the sum gives us minus 14. So it starts from minus 14. Okay. So here then the slope, we have only one slope, since here we have a constant 6 and here we have 0. Okay. Is it clear? So until 10 we have only one slope, isn't it? So until 10 we have only one slope. So we start from minus 14 and we have only one slope, which is 20 decibel per decade. Then at 10, here at 10 you will have another slope, right? So at 10 we'll have another slope, which is minus 20. So that means we'll have a constant, since we have 20 decibel plus minus 20 decibel. Okay, so we'll have a constant at this point. Okay, so this point should be at 10, not after 10. Okay, so it should be at, yeah. So yeah, at 10 radian per second. So at 10, W equals 10. So the magnitude becomes constant. What about the phase now? For the phase angle, so for the phase angle, it's 90 minus tan inverse of 0.1 W, as shown here in these calculations. Okay, so how to find it? You have just to find the angle of 2 plus the angle of JW minus the angle of 0.1 JW plus 1. Okay, so for 2, tan inverse of 0 over 2, it's 90 degrees. JW is tan inverse of W over 0, and for 0.1 JW1 is tan inverse of 0.1 W. So it seems that this phase is variable, it depends on W. So it will start from 89.4 degrees to 0 when W goes to infinity. So then you can plot these points and draw the curve. Okay, so this is the body diagram. So let's see how to use MATLAB. So the function is 20s. Yeah. So you have 20s over 20s over s plus 10. 20s Okay, so the numerator is, you have 20s, right? So this 20s, that means it's 20, 0, right? 20s is 20, the vector 20, 0, and the denominator of g is s plus 10. That means you'll have 1 for s and 10 for as the second coefficient. Then how to find g? So g equal tf, numerator of g, and here denominator of g. Okay, then we use the function body of g. Okay, so let's save and see. Okay, so we get the same. Yeah, so this is the body plot of the function g of s, 20s over s plus 10. Okay, so it starts from minus 14 as shown here. Okay, it starts at minus 14, and then here it's I cannot select the points. Yeah. So is it clear now how to use body plot? Okay, so we get the same curve as shown here. So I think I will stop here now because your quiz will start soon. Okay, so we'll have only one question. Okay, we'll have only one question. So for this, for this problem, you can use MATLAB also here to plot the body plot. Okay. So I will stop here, inshallah.
Doctor, can you hear me?
Yes, yes.
Doctor, in the quiz, if there is a question that needs to be to prove that it's stable or not, do we have to show this with calculations, or we can just do it by the calculator?
You have two ways. You can use the Routh-Hurwitz criterion. I mean, you complete the table and you prove that it's stable, or you can just find the poles. If all poles are located at the left half plane, so you can say that the system is stable. So you have two ways, okay? You can use the calculator and find the poles, or you can use the table, the Routh table.
Okay, Doctor.
Is it clear, Ahmed?
Yes, yes.
Okay, so I will stop recording now. Assalamu alaikum wa rahmatullahi wa barakatuh.